All right, so we started looking a little bit at sine and cosine. We practiced, I think we did unit circle trig a little bit last week and kind of learned the definitions. This week we're going to focus more on how the graphs look if you draw them. Okay, so first of all, these functions fall under a category of what's called a periodic function. And the reason they're called periodic is because they repeat over and over. Okay, I'll show you what they look like real quick so you can just kind of get an idea. But what you're seeing there is a wave pattern, and there's a certain amount of distance you have to go on the screen, and then that pattern is just going to repeat. And so, make that a little smaller. If you focus on what's between the two red lines, that's one section, and there's a name for it, but that's one section of the graph. If you take what's inside that one section and just copy and paste it left and right, that's what the graph looks like. Right? So anything outside those red lines, it's just a repeat of the part that's inside. So the way to kind of describe that is what's happening is the y values are going to keep repeating. For this particular graph, this is the graph of sine. The y values go as high as 1, and they start coming down to 0. They hit -1, then they go back to 0. That 0, 1, 0, -1, 0. That pattern that I just said, it's just going to keep repeating, okay, over and over. I just hit enter on your ID. And that's it. So those y values just keep repeating over a given set of x values. What's the given set of x values? It's from here to here, okay, where I just tried to show you back and forth. And I'll show you what the graph of cosine looks like. Okay, that's sine. Cosine looks almost the same. Okay, basically, well, if you had to describe that one, how do the red one and the blue one compare? If you want to maybe describe them as a transformation.
The red one's 1 to the left.
Yeah, it's a shift left or right. Either you could say the red one's to the left or the blue one's to the right, but they're just shifts of each other. That's why we study sine and cosine together, because they look almost the same. If we look at the graph of tangent, it's periodic because it's repeating the same thing over and over, but it doesn't look like sine and cosine. It's kind of these repeating curves. Right, so we'll look at that one later in the week. Okay, so the length of that interval, if I sketch this again, from here to here, between those two black lines, that section is called the period. Okay? It's the period of the function. It's basically how many lines do you have to go, how far do you have to go before the graph repeats itself. And the normal period, if you don't shift it, you don't stretch it, you don't compress it, you don't mess with the graph at all, the graph normally has to go from 0 to 2 pi before it repeats. Or if you were thinking in degrees, that would be from 0 to 360 degrees. Okay, so what I could do is ask you to graph something eventually on the calculator. and say, instead of showing me multiple periods, just show me one period on the screen. All I want to see is what's in that black box on the whole screen. So what did we just say the period was of sine? 2 pi. So if you go to your window, let's start at 0, and let's end at 2 pi. And now you're going to see what's exactly in that black box, one period. What if I did 0 to 4 pi? How many?
You double that.
I would see double it. I would see 2 of them. Now you're going to see 2 sections. There's one, it just finished, and there's the second one about to finish. There's 2 sections of it. Okay. When we sketch it by hand on paper, we're just going to sketch one section. Because we know if we can sketch one section, it just goes on forever, copies of that one section over and over. Okay. But that one section, that's called the period. Okay. Another name for the period is called a cycle, one cycle of the graph. If you do anything with electricity, has anybody studied Hertz? Maybe you know Hertz. Yeah, Hertz stands for cycles per second. So with electricity, like the kind in this room, not the kind in your car, that's direct current. I'm talking about alternating current. Alternating current runs at 60 hertz. So what that means is the electricity cycles 60 times up and down in 1 second. And if you have a device, probably not a multimeter, but something where you could plug it into the wall and you could see a picture of the electricity, you would see it cycling 60 times up and down in 1 second. If electricity doesn't run at 60 hertz, like sometimes people have a generator, and if it's a really cheap generator, maybe it would run at like 57 hertz, or maybe it'd run a little high, like 62, 63 hertz. Eventually, over time, what that would do to like a motor is it would burn it out. It might work at first, but the motor is going to be used to getting 60 hertz, and it's not getting the right electricity. So after a while, the motor is going to get hot. It's not going to run right. If you're running a light bulb or something simple like that, that's not really going to hurt it too much. Okay, but like a TV or a computer, anything with like sensitive electronics, you've got to make sure that the electricity going into it is 60. That's why sometimes they say don't run like an LCD TV or a plasma TV on a generator, because it can damage it. Now, if you have a really high-end generator, it takes care of that problem for you, and basically makes the electricity exactly the way it should be. But a cheap generator might not. All right, so when we graph sine and cosine, we really need 5 points. Where we start, where we stop, the highest, the lowest, right in the middle. If we can get those 5 points, we can make a good sketch. So those 5 points will give us a very nice picture. If you're graphing something simpler, like a line, you only need 2 points to sketch a line. To sketch a curve like this, you need 5. Now, if you look at that graph, by drawing 5 points, you break it into 4 sections. 1, 2, 3, 4. 4 sections. Well, we know to go from the start to the finish. We said it's 2 pi, or 360 degrees. Well, if I want to break that 360 degrees into 4 equal sections, how much would each section be? 90. So that's why we put a point every 90 degrees. Okay, a lot of the problems, in fact, most of the problems we do this week are going to be in radians. So every point here, you could think of it as being 90 degrees apart, because that's the units on the x-axis. On the x-axis, you're graphing an angle. On the y-axis, you're graphing the sine of the angle. Okay, so in degrees, that would be 0, 90, 180, 270, 360. So that's the name of your x-axis, angle. Y-axis, it's the trig function of the angle. In this particular problem, sine. Okay, so what we want to do is make a table of those points. Okay, let's put them in a table. Because if you want to graph a transformation of that, first you have to know where does it start. And then once you know where it starts, you can figure out where it moves to. And the 4 transformations we're going to study are the same 4 we've done with every function all year. Shifting up and down, shift left and right, stretch up and down, stretch left and right. All right, so we're going to have 2 tables. We're going to have one for the starting points for sine, and then we're going to have a different table for the starting points for cosine. Okay, 2 tables. And if you ever forget the table that I'm about to show you, you could always figure it out by going to your table and typing in those 5 x values. 0, 0, so the first point is right at the origin. Pi divided by 2. What does it look like the y value is? It's up at 1, so it's going to be the second row in our table, but we're not going to write it as a decimal. At pi, what does it look like the y value is?
0.
Yep, pi, we're back at 0. 3 pi over 2, that's the lowest point, -1. And then 2 pi is a repeat of 0. 2 pi is starting the next period, so we're right back where we started. Okay, so that's the table you're going to put in your notes, but leave it as multiples of pi. So 0, 0, and all the others. Okay, and again, that's the starting table for sine. So it's real important we get that table right, because every single problem we do involving sine for the rest of the week, that's the table we start with. So if that table's wrong, then every problem we do all week is wrong. Okay, I'm going to graph cosine, and then let's see if we can look at the graph and get the 5 points for cosine. The x values are the same. The reason we keep them the same is because we want to have an x value equally spaced every 90 degrees, okay, or every pi over 2 radians. But now, if you take the same x values and you plug them into the cosine function, you're going to get different answers than the sine function. So this table is going to be different. So let's see what it is. Let's make a picture of cosine. What did we say the period of sine and cosine are? You have to go from 0
2 pi.
to 2 pi. I'm setting my end of my window to be at 2 pi because I only want to see one section. Okay, so that's cosine. Remember, when I showed you cosine, it's still a wave. You're just seeing the down part of the wave. Okay, it would continue. Right, what does it look like the y value is when x is 0? Yeah, when x is 0, we're starting up at 1. Okay, how about a quarter of the way through the period?
0.
Pi over 2, we're at 0. Halfway through the period, we're at pi, and what's my y value there? I'm at -1, 0, and back to 1. So it's the same y values, but they're in it's kind of like a different order. Sine starts at 0.
It's opposite.
Cosine starts at 1. In tangent, I showed you the graph of that, but we're not going to talk about it today. Sine and cosine are the two graphs we go really in depth with. We're going to talk in a lot of depth about all the transformations. When we get to tangent and all the other ones, we don't go into quite as much depth. Because we're going to spend 2 days just on sine and cosine. We probably could do it in 1 day, but we'll slow it down. We'll do it in 2 days. So 2 days for just these two functions. We're going to do every other function in 1 day. So we're going to talk about a lot less stuff. Okay. If you're only going to do one transformation at a time, which is how we're going to do it for today and most of tomorrow, then that means one of these columns is going to stay the same and one of them is going to change. For example, if all you did was shift up, that doesn't have any effect on the x values. X's, that's left and right. So if you shift up, we're going to have to change the y values. We would leave the x's alone. Let's say that we shifted left. Shifting left is going to change the x values. But does shifting left or right do anything to y values? No, because y is up and down. So for each transformation, today and tomorrow, one column will stay the same, one column will change. The only way that's not true is if you do multiple things at the same time, like shift it right and up. Now you're changing it. Okay, but the homework tonight is just going to be a single transformation per problem. One transformation per problem. And honestly, since you guys have already done transformations with every function we've studied all year, you probably could do 2 transformations at the same time. So we probably could cover this section a little bit faster, but if we cover it at the pace we're going, it just gives us a nice stopping point on Thursday. I don't really want to start section 6.5 this week. All right. So now we're going to talk about a specific transformation. Okay, everything I gave you so far, that's just kind of background information. Okay, you've got the starting tables, you've got everything you need. Now we're going to talk about a phase shift. So when we studied all the other functions, normally we call this a horizontal shift. But when we study it with trig functions, they call it a phase shift. Okay, so again, phase shift, just a fancy way of saying shifting left or right. And most books and most anything that deals with graphs of sine and cosine, they're going to call it a phase shift when you shift left and right. So here's a program. And when you shift left and right, remember I told you the x-axis was your angle. Okay. Well, this program will shift in degrees. Okay. It doesn't shift in radians. But there's an example of a phase shift. In that case, I shifted right 160 degrees. Notice if I keep going and I shift it 360 degrees, can you notice that I did a shift at all?
No.
No, because you've shifted it so much now, you've shifted everything to the next period, so you can't tell. Right. So we'll play that later on and hear what a phase shift sounds like. So first of all, what does a phase shift look like as an equation? exactly the same as shifting left and right in every equation we've studied all year. It's when you add or subtract inside the function. There's a square root, that's a phase shift. There's a parabola, that's a phase shift. There's a log function, that's a phase shift. They're all shifting. Those are all phase shifts. They're all shifting which way 2 units?
Left.
Yes, they're all shifting left 2 units. Well, now we're doing the same thing with sine and cosine. Technically, you can shift by any amount you want. If you want to shift by 115.2, you can. If you want to shift by 92.88, you can. You can shift by any amount. But the common amounts that we're going to shift by are pi over 2, pi over 4, and pi. Anybody remember what those are? What's pi in degrees? 180. And then pi over 2, half of pi, 90. And pi over 4 is half of pi over 2, 45. So the common shift amounts are 90, 45, and 180. I say common because you can do anything you want, but that's what we'll mostly focus on. Because we're going to be shifting in radians, that means we're going to have a fraction. So we're going to have to deal with adding and subtracting fractions. Okay? Anytime you want to add or subtract a fraction, what do you have to have first? You got to have a common denominator. That's okay. So I put this statement more for my trig class when I teach it, because you guys should already know that. If you do x minus, minus shifts right. If you do x plus, it shifts left. It's exactly the same rule we've been following all year with horizontal shifts. Okay, so any questions on which way things are going to shift? It's exactly what you expect. All right, so once we look at the equation, we figure out, okay, we're doing a phase shift. Now we have to figure out what's going to happen to the table. When you do a phase shift, what values is that going to affect? X values or Y values? X's, right? Phase shift is left and right. So for a phase shift, you're going to be changing the X values. So if the X's are going to change, that means the Y's stay the same. Okay, so you go to your original table that you have in your notes, you copy down all the Y values. Because we're not doing any change to them at all with the phase shift. Okay, so now we need to find the new x's. Okay, to find the new x's, the big thing you have to remember is it's the opposite. Right? Whenever you do horizontal, you see plus, you might think, oh, plus is the positive direction. We go right. No, plus, you go left. So you always do the opposite. So determine what has been added or subtracted. Okay, so in the problem we're going to do, determine what's been added or subtracted. We are going to subtract pi over 2. That's what's being subtracted. Now, because horizontal shifts always do the opposite, you do the opposite. You see a minus pi over 2, you're going to do a plus pi over 2 to every x value. The reason you do a plus is because plus is going to shift it right. And that's exactly what should happen when you have that. You should always be shifting right in that format. If you said, oh, I see minus pi over 2, I'm just going to minus a pi over 2 from everything. Well, that's going to shift it the wrong way. Okay? So remember, horizontal shift, do the opposite. Okay, so we'll make a table. And the first step would be to figure out what kind of transformation is it. Well, it's got to be a phase shift. It's the only one we've learned. And anytime you add or subtract inside the function, that's your shifting left and right. So Josh, what column is going to stay the same here?
The y's will stay the same.
Yep. And can you tell me from our original table in the notes, what are the y's for sine?
For sine, 0, 1, 0, negative 1, 0.
Yep. 0, 1, 0, negative 1, 0. If that was a test problem, the way I grade it, you get 1 point for each of those numbers. Okay, so you automatically get 5 points for that table if that's all you know how to fill in. Now, to get the other 5 points for the table, we got to get the x's. I'm going to put my answers in that box, but off to the side, I'm going to do a little work. Michael, can you tell me what my x values are for sine, the original ones in the table?
The original ones are 0.
Yep.
Pi over 2.
Pi over 2.
Pi. 3 pi over 2. And 2 pi.
2 pi. Now, I see a minus pi over 2. So what am I going to do to all those original values? Add pi over 2. I'm going to do out that calculation, and the answer is going to go in the table. Okay, we don't do any decimals. We're going to leave everything as fractions. Let's start with the first one. What's 0 plus pi over 2? Which is pi over 2. Now the second one already has a common denominator. What's pi over 2 plus another pi over 2?
2 pi over 2.
Yep. 2 pi over 2. But what would that reduce to?
Pi.
Pi. It's good to write it as 2 pi over 2 because if you do, you're going to see a pattern when we're all done. Okay, next one. What's my common denominator between 1 and 2?
2.
2. So what would we multiply top and bottom by?
2.
2.
That would be 2 pi over 4.
Yep. I don't really have the space. I'll do it off to the side. Multiply top and bottom by 2. And now we have 2 pi over 2 plus 1 pi over 2. How much is that? 3 pi over 2. Okay, next one already has a common denominator. Before you reduce it, can someone tell me what you would get if you add them? 3 pi over 2 plus 1 pi over 2.
4 pi over 2.
4 pi over 2. And what does that reduce to? 2 pi. And the last one, same thing again, you need a common denominator. Common denominator again between 1 and 2. 2. Double the top, double the bottom. So 4 pi over 2 plus 1 pi over 2. 5 pi over 2. Yep. And now, if you've done this right, you should be able to read down your x column and notice a pattern. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Okay. So eventually, once you see the pattern, you can go with the pattern. You should always reduce it, okay, as for the final answer. But if you want to see the pattern, that's why I left it unreduced at first. Okay. Any questions on the table? Right. So 5 points for each x value, 5 points for each y value. the table is worth 10, and then the graph at the end is worth usually 1 or 2 points. Depends on the problem. Right, so on that grid, I'm going to make a graph. Now, for y values, it makes sense to go by ones. For x values, it doesn't. Okay? Because if you were to write these as decimals, pi over 2, that's 1.57. 3.14, 4.71, 6.28. Those are going to be very messy numbers to graph. But, what's pi over 2 again in degrees?
90,
That's 90. How much is pi?
180,
180. Pi over 2 is 90, but it's times 3. What's 90 times 3? 270. How about 2 pi?
360.
It's 360. What do you notice about all these numbers?
Going up by 180.
They go up by 90, right? They're all equally spaced. And when you graph something, you can label the axis any way you want, as long as you label it with things that are equally spaced. Okay? If you want to label something by 3s, go for it. You want to label it by 7s, that's fine too. We're going to label it using these numbers that I just circled, because they are all equally spaced. What you can't do is something like this. 3, 6, 7, 8, 12. You have to be consistent with your numbers. You're going to go by 3s, go by 3s all the way. Okay? We're going to go by 90s. But we're not going to write it in degrees. We're going to write it in radians. Right? So we've got 0, pi over 2, pi, 3 pi over 2, 2 pi, how much higher do we need? One more. 5 pi over 2. And we know those are all equally spaced, so we're good. Okay, and now make your graph. Pi over 2, 0. Pi, we're at 1. 3 pi over 2, back to 0. 2 pi, we're down at negative 1. And 5 pi over 2, back to 0. Now, connect the points. Remember that this graph is a curve, okay? So it shouldn't look like that. Okay, try to draw it as smooth of a curve as you can. And there's your sketch. The original, if I can move this, the original would have been starting at the origin. This one has been shifted to the right. How much? Pi over 2. Okay. Any questions on that? So that's a phase shift by 90 degrees to the right. All right, let's take a second and hear what that would sound like. Okay, so I'm going to play a phase shift. Anybody have a guess what it's going to sound like if I do a phase shift? No change in the sound at all?
No, it's gonna go like fast.
It's going to what?
No, it's not going to change at all.
So you think you'll hear the same thing? You won't really
It's
hear
not
it.
changing the length of it, it's just changing the position of it.
All right. So one thought is won't hear anything at all.
So this will hear something, it's not going to be different from what it was.
So you're going to hear the same thing.
Yeah.
So, okay.
I'm not that good at physics.
Any other thought what's going to happen? Well, let's play it, and what I'll do is I'll drag it from a 0 degree phase shift all the way to 360 as I'm playing it. Okay? Takes a second, it's got to connect. But I'm going to play this tone. And maybe I'll go a little lower. This will play about that tone. And I'm going to drag left and right as I do a phase shift, and then see if you can describe to me what it sounds like. Anybody hear that? Did it kind of sound like it did
It
something?
like slows down and then goes back.
Intensifies.
Now I heard, from standing here, I heard nothing. It sounded exactly the same the whole time. And that's because of where I'm standing and where the sound is playing. I'm right in the middle of the two speakers. So if you're standing right exactly in the middle, which nobody really is, you wouldn't hear much of anything. But definitely on the sides, depending on where you're sitting, you might hear different things. Like when you think it's getting quieter, like somebody, did anyone think it sounded like it got a little softer?
Yeah.
Well, where this row thinks it got quieter, for another row, that's where it's getting louder. It's kind of a, we'll do it one more time, kind of a weird effect. Again, for me, I heard nothing standing right here. I heard exactly the same thing the whole time.
What is happening?
Well, what's happening is, have you ever heard of like noise canceling headphones? Where things they sound softer because they cancel out the noise?
Yeah.
That's kind of what's happening. Okay? You're canceling out sound because there's another sound playing at the same time. Okay? Kind of a weird idea, but cars do it all the time. They have cars with noise canceling sounds to make the engine sound quieter. And I said to you, well, how can that work all the time? Okay? You all set, Colin? All right. So yeah, that's kind of what's happening. If you were to play this on a single speaker, okay, this is obviously left and right in that sound bar, but if you had a single speaker and you played about like that, okay, you would hear nothing out of the single speaker. Because what would happen is, if you look at the blue wave and look at the red wave, think of the blue wave as like pulling up, the red wave is pulling down, in this section right here. They would cancel each other out, and you'd hear no sound at all. So for certain people, if you're standing in the right part of the room, when I play this, it would sound softer. Now the problem in here is the sound is going to echo off every wall. So I can't really do it so you'd hear nothing. But if we were outside and had two speakers and the sound couldn't echo, when I play this, some people would hear nothing. Or it would be extremely soft sound. And that's basically how noise canceling headphones work. Noise canceling headphones, a little more complicated because the sound, if you're trying to cancel out noise, well, what's noise? I mean, my voice is noise to some people. But it depends, right? Noise, that's a very easy tone to cancel out because it's staying exactly the same. It's a very easily describable sound. It's a frequency of 879 hertz. But if you want to cancel out like a voice, that's harder to do because the frequency of someone's voice is constantly changing, okay, up and down. Also, the volume might be changing. Usually when you get to the end of a sentence, you talk a little softer. It's just how you speak. So some sounds are very easy to cancel out, some sounds much harder. But that's what a phase shift sounds like. Okay. What you could also do is play a phase shift, and instead of me dragging the phase shift slider, you walk back and forth.
What about, what's the other one called, the other shift?
There's a vertical shift. We're going to look at that last. There's no connection with sound to a vertical shift. That's the only one I can't really play. But if I played that right now and somebody walked back and forth, they could hear it really loud at one spot and not as loud as another spot. Okay? That comes into play like when people are setting up like a band, right? The acoustics in the room, they want it to sound good for everybody, roughly, that's in front of the stage. So that's why you stand on the stage or behind the stage and it sounds awful because the speakers aren't aimed that way and the sound is designed to be heard well in front. Hopefully with no dead spots if the room acoustics are good. That's why theaters have all kinds of special things to make sure it sounds good for everybody with no dead spots. Yeah?
Is So like a kind of like fabric that they put on the walls.
Yep.
That can like stop noise from coming, like
Yep.
from hitting it in a weird way.
Yep. So what fabric would do, or anything that's like not a hard surface, would stop reflections. So in this room, there's a ton of reflections because my voice will hit every hard surface and bounce back. That's why when I set up the mic, it's encased so that all the reflections of my voice off the back wall aren't picked up as well by the mic. But my voice still reflects off the back wall, hits the front wall, and then goes into the mic. We can't really put curtains on everything. But yeah, it would be pretty disturbing.
Yeah, you'd be like.
It'd be bouncing everywhere, yeah. All right, let's try. Let's do this one. And I'm going to change it. Actually, no, we'll do it like that. Sine of x plus pi over 4. Okay, what kind of transformation is that? Yeah, it's a phase shift, right? Because you're adding, or you could be subtracting inside parentheses. What letter stays the same for a phase shift?
X or Y.
The y's stay the same. So we've got 0. Can people remind me, what are the other y's for sine?
1, 0, -1,
1,
0.
0. Okay, 5 points for your y's. X's. What are my original x's for sine?
0, pi
Yep.
over 2, pi, 3 pi over 2, 2 pi.
3 pi over 2, 2 pi. Hopefully by the end of the week you'll have written that so many times you just know it. And now, what do we do to all the original x's to get the ones I'm going to put in that table? Right. Subtract everything, or subtract pi over 4 from everything. Now, I'm just going to do the first 2 or 3, and then I think you'll see the pattern, and we won't have to keep going. First one's pretty easy. What's 0 minus pi over 4? Negative pi over 4. Now the next one, pi over 2 minus pi over 4. What's the common denominator?
4.
4. Right? Common denominator it can't be smaller than anything you have. It has to be bigger. So multiply by 2, multiply by 2. Okay. Colin, can you just check? If you multiply 2 times pi, you get 2 pi. 2 times 2, you get 4.
Pi over 4.
So what do you get when you subtract?
Pi over 4.
Pi over 4. Okay, let's do one more, but then I think after that you'll see the pattern. Pi minus pi over 4. Common denominator again.
4.
So let's multiply the bottom by 4, top by 4. 4 pi over 4, take away 1 pi over 4.
3 pi over 4.
Get 3 pi over 4. Now, look at the number in the numerator. Negative 1, 1, 3. What do you think the next one is?
Negative.
Zero.
Well, what's the pattern? And it's written out. Negative 1, 1, 3, plus 2, plus 2.
Oh.
So it would be
Delta my guess.
5 pi over 4. And what about the last one? 7 pi over 4. Now, if we were graphing beyond one period, what would the next one after 7 pi over 4 be?
9.
9 pi over 4, 11 pi over 4. The pattern would continue. If you don't see the pattern, that's fine. Do the subtraction, find the common denominator. 6 pi over 4, take away 1 pi over 4, 6 take away 1, there's your 5. So you don't have to see the pattern. You can just do the common denominator every time. Okay. 1 point for each x, 1 point for each y. Okay. 10 points for the table. Let's make our graph. Okay. First one is negative pi over 4. These are all equally spaced, and they always will be. So you're always going to use those as your labels. X, that's y. Now, the next one after negative pi over 4 is what? Pi over 4. Where would pi over 4 go? Where would I put the label pi over 4?
That's 0.
At 0?
I don't know.
Well, the axis is always what number?
0.
0, you said it. The axis is 0. You can't put pi over 4 there. That's the axis.
Would it be halfway in between negative 1 and 0? No, never mind. That
Well,
won't
it's
work.
going to be the positive version of negative, so it's going to be
Yeah.
right there.
It's going to be right there. So now, here's the important thing. The next label is 3 pi over 4. Where does the next label go? You want to see where the
On the fourth one.
right? It can't go here. Because if you put it there, you're not labeling it consistent. You put a label, you skipped. You put a label, you skipped. You put a label, you skip. And what was the highest one? Do we need 7 pi over 4?
Yeah.
So I need one more. Put a label, skip, put a label. Okay. If you made a mistake and you put 3 pi over 4 right next to pi over 4, what your graph would look like is something like that. It would look really squished in part of it because you put things together that shouldn't have been. And then you have things that are more stretched out. Okay, that's the only time that that happens, when you have to skip a label because of the axis. You can't just say the axis isn't 0. It is 0. It's always 0. So you have to skip over it. All right, so now graph all your points. Let's see, negative pi over 4. We're at 0. Oops. Negative pi over 4, we're at 0. Pi over 4, we're up at 1. 3 pi over 4, back to 0. 5 pi over 4, that's the low point for the period. And 7 pi over 4, back to 0. That graph looks nice and smooth. Looks good. Okay, so we're going to look at 2 transformations. That's the hard one, the phase shift. Because the arithmetic you have to do involves all fractions. The last transformation we're going to look at is super easy because all you have to do is arithmetic with 1s and 0s. No fractions, no numbers bigger than 1. And that's the vertical shift. So, vertical shift. You guys already know this. If you already know that, you don't need to write it, don't write it. Vertical shift translates up and down. Where is the vertical shift in an equation? It's the number at the end. We did that with square roots. It's a square root shifted up 2. That's a log function shifted up 2. Oh, works the same with sine and cosine. What's the difference, though, between a vertical shift and a phase shift?
No parentheses.
Well, I got parentheses in. I got them in that one.
It's outside.
Exactly. It's outside the parentheses. That's the key. It's at the end, and it's outside of parentheses. So even if they throw parentheses in like this, that's still a vertical shift. It's outside parentheses. And with vertical shift, you do exactly what you would expect. Positive is up, negative is down. Don't do the opposite. When you do the opposite, that was phase shift. Vertical shift, you do exactly what you see. And if we're going to shift up and down, what values does that change?
Y.
Changes the y's. So that means what stays the same?
X.
X's. It's always great when the x's stay the same because those are the messy numbers. That's the pi over 2. This time, every single problem we do for a vertical shift today, I'll tell you the answer to your x's. 0, pi over 2, pi, 3 pi over 2, 2 pi. Every vertical shift problem in the homework, I just told you the answer to the x's. They don't change. To find the y's, all you have to do is add or subtract whatever that number is to all the original y values. You remember,
What do you do? Oh no, you don't do the opposite.
no, don't do the opposite. Don't do the opposite. So if you have a problem that has a +6 for a vertical shift, you're going to add 6. If you see a -10, you're going to -10. And remember, the arithmetic here is super easy. You're taking a 1, a 0, or a -1, and you're adding a number to it, or you're subtracting a number from it. And so we'll finish up with 2 vertical shifts. We'll do one up, one down. And one of them I'll do with sine, one of them I'll do with cosine. Okay, so let's start with the cosine. Okay, first thing, how do we know that's not a phase shift? Because phase shift still uses addition.
Parentheses.
Okay, what if I put parentheses like that?
Outside.
Right, it's outside. The only way I could make this a phase shift. Now that's a phase shift. But that's a weird phase shift. I said with a phase shift, we're usually going to do pi over 2, pi over 4, and pi. Not that. Okay. So, since that's a vertical shift, what stays the same? Which column?
Yes.
X's. Can you tell me what my X's are, Kevin?
0, pi over 2, pi, 3 pi over 2, and 2 pi.
All right. Now, off to the side, I'm going to put my original cosine, not in the table. But can someone remind me, what were my original y's for cosine?
1, 0, -1, 0, 1.
Yep, 1, 0, -1, 0, 1. And what are we going to do to all of those?
Give me 2 plus 2.
Plus 2. So 3, 1, 3, 2, 1, 2, 3. And that's it. So it's a lot easier with the y's. And what's the highest y value I have there?
3.
3. So when I label it, I need to go up to 3. Do I have any negatives on the y-axis? Nope. And what am I going to use for my x-axis labels?
Those values right there.
Yeah, those values right there. You don't have to label 0 if you don't want to. I know the axis is 0. But everything else, you do need to label. What if you don't label an axis? What do we always assume we're going by?
1.
We're going by ones. So technically on the y-axis, if you didn't label it, I wouldn't take anything off. If you didn't label the x's, I wouldn't. Okay. Let's graph our points. 0, 3. Pi over 2, 2. Pi 1. 3 pi over 2, 2. 2 pi 3. Now, should I draw that as a V? Should it look like this?
No.
No. It's It's that section right there. So it's kind of like a V shape, but it's curved. And it would continue on. So there's your cosine shifted up 3. This one, let's just make the table. Okay, first of all, how do we know that's not a phase shift?
Some parentheses.
It went up.
Again, can we be more specific then? Because I can, so there's parentheses, but it's still not a phase shift. Right, the X and the number are not grouped together in parentheses. Okay, so what column stays the same for a vertical shift? X. X's?
0, pi over 2, pi over 2.
And now, what are we going to do to all the Y values?
-3.
-3. So we start at 0, 1, 0, -1, 0. What do you get if you minus 3 from all of them?
-3.
Yep.
-2. -3. -4. -3.
That's it. There's your table. And now you just graph it. Okay? So those are the 2 shifts. Somebody asked before, connection with sound on this one. There isn't one. So that leaves the 2 stretches for tomorrow. Horizontal stretching and compressing, and vertical. Okay, homework is those 7 graphs. I already have them written out on a worksheet. So if you lose the worksheet, you can just go online and see what the problems are. But I'm going to give you those on a worksheet.